Hello, good afternoon to everybody. I am Abu Jahid, your TA for ELG 4125 course. So today I'm gonna present some problems on power transformer following to the second DGD. In this lecture, I will cover some examples so that you can do the maths. So here is the per unit quantity. So it can be defined as the actual quantity over the base quantity. So in power system we use resistance in ohm or impedance in ohm and the voltage in volt or current in ampere, or transformer is usually rated in kVA or volt ampere. So all the unit can be expressed in the single unit is called a per unit quantity. So yeah, so if we want to present all the element in the same platform, then we have to use per unit quantity, and it can be defined as here. So and the base current, so base value is the reference value. So the base current can be defined as this is the apparent power or the volt ampere divided by voltage. So if we cut here voltage, then only remains the ampere. So it's LN means line to neutral is for single phase, and similarly we can define it for three phase. And the base impedance or the base resistance, whatever the reactance, it can be expressed by this equation. So Z can be expressed as B over I. So and it can be expressed in this way: B square divided by volt ampere rating. So it's just a formula. We need this to do some maths on power transformer. And so here, so this equation is applicable for one element. So whenever several elements are involved, like more than one transformer or the machine, like a generator or motor. So whenever the more than one elements is involved in a circuit, in a whatever the single phase or three phase, then we have to use a different formula. Here it can be expressed is here. So you see the new per unit impedance here is a per unit. New means the older one is given to the reference. So and the new can be expressed as this one. So old means the given value, and whereas the new means the actually the base value. So let's start this. So we got three formula here. Here is the one, here is the two, and here's another three. So let's start. So here is shows that there is a three zone over here in the figure: zone 1, 2 and 3. So there is a two transformer here, transformer 1 and transformer 2, and the rating are given here. So in the maths, the problem is said that the base value, we have to use the base value 30 kVA kilovolt ampere and 20 to 40 volts in zone 1. Here we have to consider the base. We see that the transformer 1 has the same value, is 30, and 240 is the primary side. Now we have to draw the per unit circuit and determine the per unit impedance and the per unit voltage, and also the current in the real value in the ampere. So let's see the figure. Here is the generation side. It's a for single phase. It's a single phase circuit. So this is why the phase to line voltage is 220 volt, and it's a reference one. This is why it's called, it's 0 degree. And it's a step up transformer here, because you see there's a 240 to step up is just two times step up. And this is a transmission line, the zone 2, this is a transmission line, it's a wire. And another transformer is here. Clearly shows that it's a step down transformer, and here is the load. This is the utilization section. So here's the zone 3. And okay, now let's start. We have to draw the per unit circuit. So here you see that there is a more than one element is here, so we have to apply this formula because there is a two transformer is here. So yeah, so that there is a several components. So yeah, there is a several component here. Now let's start. So base 1 is already given in the given problem. So it's 30 kV, the A's base for zone 1 is 30 kVA and the base value of voltage is 240 volts. Now we have to determine the voltage in zone 2 as well as zone 3. So in zone 2 it can be defined as, so here it says that, so when the moving across the transformer, so we are planning to find the base value in zone 2 here. So we have to cross transformer T1. So the voltage base is changed in proportion to the transformer voltage rating. That means the transformation ratios of 480 by 220 in last DGD we show that the transformation ratio can be expressed as here. Transformation ratio, if it is K, then can be expressed as secondary turn, or this is the primary turn over here, or it's a secondary voltage or the primary voltage. So here is the transformation ratio, the secondary one is 480 and the primary is a 240, and this 240 is the base value over here because in the question 240 volt in zone 1. So here is the base value, so we have to express this is the base value and this can be changed for the proportion of the transformer voltage rating as it is clearly mentioned in the question. So here in the zone 2 we got 480 volts, and similarly in zone 3 how can we do that? So here is the base voltage, what is get the value is 480, is the base voltage 480 over here, and the transformation ratio is secondary side voltage over primary voltage, so it's 115 divided by 460, and the base value in this zone 2 is, this is the 480, this is the 480, and we got 120 volt over here. Similarly, what is the base impedance in zone 2 and 3? So in zone 2, the according to the formula, go up, here is the base value, so it can be defined as voltage square divided by base, this is base kVA rating or volt ampere rating. So here there's a formula in the zone 2, so it's 480 square and is base, so and the all over the circuit the base volt ampere is always same as 30, is 30 kVA, so it's here, and similarly in the base 3, what is the base voltage is here, we found that it's 120 according to the formula, 120 square divided by 30 the 30,000. So here you get the base impedance over here. So now what is the base current? You see we have to find out something. So all the circuit in the base value, okay, go down. So in the base current can be defined as this value is volt ampere divided by voltage cut, and then only remains the ampere. Here we got the 250 ampere as the base value. Now we have to find the per unit value of all component here, transformer 1, transmission line, transformer 2, and then load. So now here's the transformer 2, because the transformer 1 is already rated in base value, is in per unit value, sorry, my bad. So here in transformer 2, the according to the formula is over here, this is the per Z power unit is a given value, and then old mean, I mean the given, this is a given value, old means the given value in the question, and here is the new value mean the base value. Okay, let's go. So according to the formula, here we see that point 1, where is the point 1 here? transformer 2, here is a 0.1, this value is 0.1, and this is the old value, I mean the given in the question, so it's 460 over here, because 460 here, and then the base value for 2 is 480, is already we found this 480 is here. And what is the kVA, what is the volt ampere rating? So go to the formula is new and the old. New, I mean the base value, this is the new value is 30,000, and what is the old value is given in the question paper. Here is the 20 kVA, so it's 20,000 volt ampere. So here is the per unit value. So we can do it other way, because there may arise a question why we use this voltage, not this one. So we use the same one. If we use 115 here, you see, if we 115 here, then we have to use the base value in the zone 3, because you see this side falls under the zone 2, and this side, this secondary side, this low voltage side is fall under the zone 3. So if we use 115, then we have to use the base voltage for zone 3. What is the base voltage for zone 3? Is 120, and you see here we use 120. If we use for zone 2, then is zone 2 is 460 in zone 2, and what is the base voltage in zone 2? This is the base voltage in zone 2 is 480, so we put it here 480. So we got the same result over here. So now what is the transmission line per unit voltage? So we know that per unit value is the actual value divided base value. So in the transmission lines falls under the zone 2, the real value is, actual value is 2 ohm, and what is the base value in the zone 2? The base value is 768. So we put it here 2 actual value, and the base value in the zone 2 768. So we got the per unit value of transformer T2. Transformer T1 is already given in the question, and transmission line we already got. Now we only remains the load. Here is the actual value is over here. So now just similarly the actual value for the load in zone 3. So actual value is given in the question, and the base value over here is the base value in the zone 3. Just we got the per unit value. So now we have to find the current over here. So in per unit current, what we can do is voltage divided by the impedance over here, the impedance over here, and the impedance here, and the impedance here. So all the four terms are in series, so all are connected is here. This is the transformer 1, transformer 2, this is the transmission line, and this is the transformer 2, and this is load voltage, and no resistance is here. This is why it's only the imaginary term, I mean the reactance term only, and in jet load you see there is a board term is here. So we got this answer in polar form. And so what would be the actual value of ampere? Because in the question paper we have to calculate the load current in ampere. So now let's go. So in the actual value, this is the per unit value of current. So what is the actual current? So we know per unit value equal actual value divided over base value. So if we want to find actual value, then we have to multiply per unit value times and base value. So here is the per unit value, this is the per unit value, and what's the base value? So base value is 250. Here is the 250 is the base value in the load side. So here we got the actual value in the load. So this is the actual load current. So load stays in the load, falls under this zone 3. This is why we use the current in the base 3 is 250 over there. So now we have to draw the per unit circuit. So go to the single phase circuit. We have four components. This is the generator, this is the transformer 1, transmission line, transformer 2, and then load. So all of the below. So here this is a generator, so there is a neutral line, there is a reference line. So where do you get the value? Because in generator you see the value is 220, and what is the reference voltage is 241 in zone 1 it's given. So if we divided by actual is 220 divided 240, the base reference in the zone 1 is in the zone 1, so we'll get 9167 per unit. And then there is the transformer T1 is given in the question is a 0.1, and then transformer T2 we just found over there. Where is the transformer T2? Yeah, here is the transformer T2. What is the transmission line? Transmission line is 0.2604. It's the transmission line 0.2604, and then transformer T2, and the load is here is the load per unit value. So this is the all the per unit diagram. Okay, so now similarly we can do it for three-phase transformer, three-phase system. So for single phase, now we'll see for the three-phase transformer the similarly. So this is the kVA for three-phase. If we divide it by 3, then we get the single phase value, and the current is like the similar one. But here is the difference is that this is the line to line voltage and this is the line to neutral. So in Y connected circuit it can be defined as P line to line is root 3 times of line to neutral voltage. So similarly we can here is the equation is given here. So if we put it there, then we'll get this equation. So equation is similar to this: Z base equals B square over kVA rating. So now let's see an example. Here is a 3 there is a 3 transformer is rating of 25 kVA. So here's the step down transformer is there connected in delta and Y. So short circuit test is done on the high voltage side, I mean this side is delta side, and now this given value is line voltage, short circuit, line current, and the three-phase power is there. Now we have to determine the per unit equivalent circuit of the transformer. Okay, let's start is the solution. So if we consider the Y connection equivalent circuit, so we'll validate our result in both way for Y connection. So for star connection or mesh connection, we'll get the same result. Okay, let's start. So now what is the line current is here 1.26, and what is the voltage? This is the phase voltage, because you see the line voltage is there 2010 volt is there. So what is the phase value? This is the phase value, single phase value. This is the line to line for three phase current. So if we divide it by 3, then we'll get the single phase voltage. So now we express as a single phase. Okay, so because in Y connection we see that the current remains same, the line current and the phase current remains same, but the phase voltage is can be defined as the line voltage divided root 3 times. So here is the impedance of transformer, and this is the transformation ratio, because you see the transformation ratio because it's the line voltage is given. So yeah, so this is the root 3, and okay, and the base base volt ampere is given here is 25 of transformer. Yeah, so 25 base value. Now if we divided this, we'll get the phase voltage is there. What will be the base, what will be the impedance? So just V divided I. So here's a V and this is I. We'll get the ohmic value. Okay, so now in the question paper there is a three-phase power is here 912 watt. So for single phase we just divide it by 3 and we got the single phase power. And it, and what the resistance, because we defined P equals I square R, it's a copper loss, so I is 1.26 and we'll get the R value, and reactance can be defined as here. Sorry. So here we got the every value here. Excuse me. So Z can be expressed as R plus JXS. So here we got the value here, and yeah. So now the base volt ampere is there. So in the high voltage, what can it define? So just this is just divided by, you see there is a high voltage side is 34500 34,500. So in phase value it can be just divided by square root 3 and we'll get this a single phase in the high voltage side. So what is the base base value in the high voltage side? Just follow the same formula. It's B over is B based square divided by volt ampere. So yeah, so it's just square divided by volt ampere, we get the base value. Now the per unit value can be defined as the actual divided by base. Here is the actual, here is the base, just go, and here's the per unit value. So this is the answer. If we put the value over here, we'll get the equivalent circuit in per unit. So we can validate our result using delta connection circuit. So in the delta connection, this is not divided by 3 because we know that for delta connection uh, V line voltage equals V phase voltage, so no divided is there. So difference is only the current value. So here is the line current can be expressed as root 3 times into phase current. So in the question, this is the line voltage is there. So in the phase, what I have to do, just divided by line current divided root 3, and then I'll get this current. This is the phase voltage, so this is the impedance, actual impedance. Then I have to find, like similarly I have to find P equals I square R. This is three phase power, so this is the R. Now the current expression is different. Now find the reactance value and then the actual value of impedance. So, and the base kVA is there and the high voltage side voltage is there, and so in the high voltage side we just find the base value, and similarly you just find the per unit value, just actual divided base. So we got the same answer over here. So 0.12, you see, so same answer is here. So whatever we use the Y connection, either Y connection or delta connection, we always get the same result. So I would suggest to just follow this which one you seems to convenient. So Y connection equivalence circuit is, I think, is a good for doing an example. Okay, so now let's start with see another example. Our third example here is for three phase circuit. So the circuit diagram is given here. What you see, there is a generation unit, there is a transformer one. Definitely it's a high voltage transformer. The kVA rating is given here, and it's a region 1, it's a region 2, it's a zone 2. So you see is nothing but a transmission line, and there is another step down transformer, and there is a two parallel load is connected there through a switch, just a switch. And here you see Load 1 is just inductive load, because this is the power factor angle is positive, and this is the capacitive load because of negative sign. So there is a two in this is the inductive load and this is the capacitive load are connected in parallel. Now we have to find per unit per phase equivalent circuit, and then B, when the switch is open, the load 2 is disconnected from the circuit, and then we have to find real power, reactive power, and the apparent power, and as well as the power factor. Now in question C, when the switch is closed, these two are in parallel, then we have to once again we have to find real power, reactive power, and apparent power, and the power factor as well. And in the fourth one, we have to find the transmission loss, that is I square R, in the system when the switch is open and the switch is closed. So both cases we have to find the transmission loss and the effect of adding load on the system. So we have to also make a comment what happen if we add the load 2 on the system. Okay, so first of all we have to define the per phase equivalent circuit, and you see the generation unit is a generator unit is a 480 volt and 60 hertz. This generator is operating in this rating. Okay, so all the kVA rating or the base voltage, base value in all the three regions are given here, so we don't have to find the uh, base value. And one more thing, here's a one more component, like the two transformer is connected, then we have to use the above formula. Yeah, we have to use this formula because several components are involved here. Okay, go down. Yeah, okay, so first of all we have to consider the base value. So for example, if we choose the base value in the region 1, so it's 1000 kVA in the region 1 and the base voltage is 480 in the region 1. So what is the base impedance here? This is the for three-phase circuit. Yeah, it shows for three-phase, sorry, three-phase. So is 3, and this is the single phase, this is the one phase voltage. So if we divide it by 480 divided root 3, we'll get 277, and then this is 3 times. Or if we just use this value, you can we can put it directly over here. Okay, so we'll find this is the base value is there. And what is the base value 2? Here is the formula is same, and the kVA rating is same for the all over the circuit. And the secondary in the region 2, what is the voltage is, if we divide it by, this is the all of the line voltage, you see it's a line voltage is given there, B line, V line. So just divided by root 3, you'll get the phase voltage, and this is the 7967. If we divide it 13,800 divided by root 3, we will get this value. And then the third reason just 480 divided by just a similar one, we will get this base value in the all three reason. Now we have to find the per unit value here. Okay, so per unit value for transformer 1 is already given in the question because we already choose the reference. So according to the formula, whatever you find resistance or reactance or impedance, the formula remains same. So for the reason 2, the R here, reason 2, you see for there is a transmission line is there, and also in the second transformer. So for the transformer, the R is 0.02 and reactance is 0.085. then we have to express in the base value because it changed from transformer 1 to transformer 2. So yeah, so this is the R 0.02 here, this is the 0.02 102, and then all the value just put over there. There's a similar formula. It's a old and this is the new. Old means the given in the question. In the reason to, all the voltages are same. And the base, what we choose the base value is 1000 kVA in the reason 1. And what is the value over here? The base value is 500 for transformer 2. So yeah, so here's this 1000 divided by 500. This is the new and this is the old. There's a similar formula over there, and x2 in per unit can be defined as similarly. So, and what about the transmission line? The same one, we know the actual value divided by base value. What is the actual value? Go in the main circuit. Here is the actual value is the ohm, and what is the base value in the region 2? This is the base value in region 2. So just divided actual and base value, will get this in transmission line. And what about the load? The load is given here. It's a 0.5 angle 3687. And what is the base value uh, in the zone 3? It's because the both load are fall under the region 3. So in the region 3 the base impedance is here 0.238. So yeah, so the per unit value for per unit value for load 1, the actual value divided by base in the region 3. Region 3 is there 0.238. Okay, we'll get this value. And what about the load 2? The actual divided by base 3, because the impedance, because all the load 2 are in the zone 3, and in zone 3 the base value is 0.238. Okay, so now we'll draw the per unit. So here is the generating unit. This is 1 because you see this is the real value is 480, and where is the base value? We see the base value is 480. So actual divided by base, so we'll get 480 divided by 480, we got 1. And then transformer T1 per unit, we just derive over in the upper base. So in the transmission line, transformer 2 and the load 1 and load 2, all the value are derived here. And now we'll go to the second part. When the switch is open, this switch is open, so this is no more connected to the circuit. So if we what is the total impedance? Just sum all of the items. So yeah, if you add all the things, we'll get this. And what is the current value in per unit? I equal V by ZT. Okay, so here is the current value. So what is the load voltage? B equal IZ. So you see here is the current I, and what is the Z load? Load is only 1 because this side is open. So load is, this is the Z load. So load, you see this value is used here because the voltage across the load is here. And so what is the actual voltage? So if we multiply the base value, what do you choose the base value in the question? 480. So if we multiply the per unit value into the base value, we'll get the actual value. And similarly, what is the power supply to the load? This is the I square R. This is the per unit value. I, this is the I. What is the R? This is the load, this is the R, and this is the reactance part. This is the R and reactance. So I square R, and what is the actual value? Just multiply the base value, per unit value times the base value. This is the base value, 1000 kVA. So we'll get the real value. And the power supplied by the generator. So this is the real power. This is the real power. Is a VI cos theta. B is the all of the values per unit. B value is 1 here. B is the 1. I is 0.4325, and cos theta is 41.2 because the power factor angle 41.2. And similarly VI sin theta and the kVA rating. This is all the power supplied to the generator, and this is the power across the load. Here we can see that the generator supply 0.325 per unit, whereas the receive power is 0.314 or 314 kilowatt. So here you just, this is all the value in per unit, this is all in per unit, and this is the actual value. You just multiply by 1000 kVA, just we will get the actual value. We see that in the load there is a 314 kilowatt load is transferred, whereas the generator supplied is 325. So there is a loss inside the transmission line and the transformer. So this is the power loss happened because the power loss is 325 minus 314. Okay, and so what is the power factor? So power factor is just only a cos theta. So theta is 41.2. It's a lagging power factor because why is lagging? Because the load is inductive load. So inductive load causes the lagging power factor. Yeah, this one is lagging. So now in the third part, when the switch is closed, then these two load are in parallel. So we have to apply the parallel formula. Is Z1 Z2 divided by Z1 plus Z2. So the total impedance will be, this is for transformer 1, transmission line, transformer 2, and then this is two load in parallel. So yeah, we the total load impedance is here. Then the current is I divided B over Z, and the load voltage is similarly I Z load, but note that this jade load, this is the jade load. So if we just use the rectangular or Cartesian form, we'll get this value. This is the similar value, this is the similar one, and we'll get this value. And what is the load voltage? Just this is the 975 per unit value, just multiplied by base, we'll get the actual value. Similarly, I square R, this is the R value, and what is the I? This is the I, here is the I, okay, this is the I square, and if we multiply, this is the per unit, and if we multiply 1000, then we'll get the actual value. And what is the power supply to the generator? Similarly, pi cos theta, what is the power factor angle? Is 5.6. So yeah, so pi cos theta, pi sin theta, and the power in, and the volt ampere, the apparent power is volt ampere, is a point, just B and I 0.371. So if we multiply 1000, we'll get the real value. And what is the power factor? The power factor is cos theta, cos 5.6 degree is 0.995. So it's not that. So in the, for example B, when the switch is open, this is the capacitive load, so this is not connected to the load. What is the power factor? Power factor 0.752. And when the load, when the switch is closed, I mean the capacitive load is connected, then we found that the power factor is getting improved. So what is the improvement? It's a 0.752 to 0.995. So what we can see that the whenever we just add the capacitive load in parallel to the inductive load, the power factor is getting improved, and it is clearly evident from this example. Now we have to find the transmission loss. So transmission loss occur in the transmission line. So when the switch is open, this is the transmission line, this is I square R. Switch is open, I'm in the case 2. Here is the current value. What is the current value? 0.352. What is the, and the transmission line loss, in the transmission line, this is R, this is X. So go down. Yeah, this is the I square R, and this is the R. And if we multiply 1000, then we'll get the real value, I mean the actual value. And when the switch is closed, it would be case for 3, I mean C case. What is the current value? Because when the switch is closed, the current is 0.371. This is the point 371 square, and the R remains in the transmission line same, and if we multiply by 1000 we will get the real power. And we have to make a comment. So comment is that when the load is connected, as I earlier said, load 2 is the capacitive load is connected parallel to the inductive load, so the power factor will getting improved. So here is our comment. So this is all about power transformer. Thank you very much. Have a good day. Bye bye.